Quantum leap, Northeastern University researchers unlock 1000% speed increase in electronics with new material discovery. Date, July 1, 2025. Location, Northeastern University, Boston, Massachusetts. In a groundbreaking development that could redefine the landscape of electronics, researchers at Northeastern University have unveiled a method to achieve a staggering 1000% speed increase in electronic devices. This innovative research, led by Alberto De la Torre and published in the prestigious journal Nature Physics, focuses on a technique called thermal quenching, which manipulates the quantum material 1θs2 to oscillate between conductive and insulating states at unprecedented speeds. The discovery: thermal quenching. The core of this breakthrough lies in the ability to switch the electronic state of the material almost instantaneously using controlled heating and cooling. By applying light to 1θs2, researchers can induce what's termed a hidden metallic state, which had previously been stable only at cryogenic temperatures. This allows the material to conduct electricity at room temperature, opening up possibilities for electronic devices to operate at terahertz frequencies far exceeding the current gigahertz standards. Alberto De la Torre, the lead researcher, explained, processors currently function at gigahertz speeds, but with this discovery we can transition to terahertz speeds, enabling a quantum leap in electronic performance. The implications of this technology could be monumental, potentially replacing traditional silicon-based components with smaller, more efficient quantum materials. Implications for electronics. The ability to control material properties with light represents a significant advancement in electronic design. Traditionally, engineers have relied on separate materials, conductors and insulators, requiring complex interfaces. This discovery simplifies the process by using a single material that can be toggled between conductive and insulating states as needed. Gregory Feet, a co-author and professor of physics at Northeastern, noted, everyone who uses a computer has faced moments of frustration with loading speeds. With this technology, we are on the verge of creating devices that operate at the speed of light, controlled through light. This advancement aims to alleviate the engineering challenges associated with current semiconductor technologies, which have reached physical limitations in terms of density and efficiency. Parallel advances, University of Wollongong breakthrough. Simultaneously, a research team at the University of Wollongong UOW has made significant strides in the field of quantum materials. Their study, published in Advanced Materials, introduces a novel design concept through entropy engineering to realize the quantum anomalous Hall-QAH effect in a one-atom-thick magnetic material. This development allows electricity to flow seamlessly along the edges of the material without energy loss, potentially paving the way for ultra-efficient electronics and quantum computing applications. Distinguished Professor Xiaolin Wang, who led the UOW research, emphasized the significance of their findings, stating, "This method not only reshapes the electronic bands but also opens a stable gap essential for real-world quantum applications." The implications of UOW's research extend to various applications, including devices that do not overheat and can retain power for extended durations. A new era in electronics. Both Northeastern's and UOW's discoveries signal a pivotal shift in the field of quantum materials and electronics. While Northeastern's research emphasizes thermal quenching for rapid state switching, UOW's focus on entropy engineering offers a complementary approach to enhance electrical conduction efficiency. Together, these advancements contribute to the overarching goal of developing energy-efficient high-speed electronics, marking a significant leap forward in quantum technology. As 2025 marks the centennial anniversary of quantum mechanics, the timing of these breakthroughs highlights the urgency for innovation in addressing global energy consumption and technological advancement. The synergy between these two research efforts underscores a collaborative approach to solving some of the most pressing challenges in electronics and computing. Future prospects. The potential applications of these discoveries are immensely promising. From faster processors and computers to more efficient energy systems, the landscape of electronics is poised for transformation. Researchers foresee a future where devices are not only faster but also more sustainable, addressing the global demand for energy-efficient technologies. In summary, the groundbreaking research from Northeastern University and the University of Wollongong represents a monumental step toward realizing next-generation electronics. The integration of quantum materials into practical applications signals an exciting future for the semiconductor industry and quantum computing, with profound implications for technology and society at large. The recent discoveries by researchers at Northeastern University and the University of Wollongong represent significant advancements in the field of quantum materials with the potential to revolutionize electronics. Here are some counterintuitive insights derived from the content. 1. Thermal manipulation of quantum states. The idea that controlled heating and cooling can switch materials between conductive and insulating states is counterintuitive to conventional electronics, where heat generally leads to inefficiency and component failure. The researchers at Northeastern University achieved this through a process called thermal quenching, suggesting that heat can be harnessed as a tool for improving electronic performance rather than as a detrimental factor. 2. Single material functionality. Traditionally, electronic devices require a combination of conductive and insulating materials, which complicates design and manufacturing. The research from Northeastern indicates that a single quantum material can serve dual purposes, blurring the lines between roles typically assigned to different materials. This simplification challenges the long-standing paradigm of needing distinct materials with engineered interfaces. 3. Stability at higher temperatures. Quantum materials have often been associated with extreme conditions, particularly low temperatures. The fact that Northeastern's breakthrough allows for stable conductive states at near-room temperatures is particularly surprising, as it suggests that quantum effects can be utilized in everyday applications without the need for complex cooling systems. For the entropy engineering, the concept that manipulating entropy within materials can lead to the creation of a superhighway for electricity seems paradoxical. Typically, entropy is associated with disorder and inefficiency, however. The researchers at UOW demonstrated that introducing randomness at the atomic level can enhance electrical conduction without energy loss. This finding flips the script on how disorder is perceived in material science. 5. Quantum anomalous Hall effect. The ability to achieve a quantum anomalous Hall effect in a one-atom-thick material challenges previous assumptions about size and functionality in electronics. The notion that a material only one atom thick could facilitate perfect electrical flow without energy loss contradicts the conventional understanding that more substantial materials are necessary for efficient conduction. 6. Potential for ultra-efficient electronics. The research posits that future devices could not only be faster but also significantly more energy efficient, possibly functioning for extended periods without overheating. This counters the typical expectation that faster electronics invariably lead to higher energy consumption and heat generation. 7. Light as a control mechanism. The use of light to manipulate material properties is a notable departure from traditional electrical methods of control. This integration of photonics into electronic material science presents a novel approach that may redefine how we think about and design electronic devices. 8. Revolutionizing device design. The breakthroughs suggest a fundamental shift in how electronic devices are conceptualized. Rather than layering different materials to create complex devices, the future may lie in innovating within a single material framework. This simplicity contrasts sharply with the complexity of current silicon-based technologies. 9. Global energy consumption impact. While many technological advancements are often viewed through the lens of performance enhancement, the focus on energy efficiency in these findings presents a compelling argument that future innovations can address significant environmental challenges. This approach emphasizes sustainability alongside speed and efficiency, which is often overlooked in favor of sheer performance metrics. 10. Interdisciplinary collaboration. The findings underscore the importance of interdisciplinary collaboration in scientific research. The integration of concepts from physics, materials science, and engineering to achieve these breakthroughs reflects a growing trend in academia that may lead to more unexpected solutions to complex problems. These counterintuitive insights highlight not only the innovative nature of the research but also suggest broader implications for the future of electronics and materials science, challenging existing paradigms and opening new avenues for exploration and application. The recent breakthroughs in quantum materials research from Northeastern University and the University of Wollongong UOW mark a pivotal moment in the evolution of electronics, particularly concerning speed efficiency and the potential for transformative applications across various technologies. While the headlines around these discoveries may focus on the impressive 1000% speed increase for electronics and the innovative approach of entropy engineering, several critical aspects of these findings are often overlooked but deserve attention for their long-term significance. 1. Thermal quenching and its implications for quantum control. The Northeastern University team's use of thermal quenching to switch the quantum material 1θs2 between conductive and insulating states is a considerable advancement. The ability to manipulate the electronic state of a material using controlled heating and cooling can lead to significant improvements in how electronic devices operate. Many people may not grasp the profound implications of this method. Traditional electronics rely heavily on silicon, which has limitations in terms of speed and efficiency as device sizes shrink. The ability to switch states almost instantaneously could lead to the creation of devices that operate at terahertz frequencies, which are orders of magnitude faster than current gigahertz technologies. This transition is not merely about speed, it opens up entirely new realms of computing capabilities, potentially enabling real-time processing of vast amounts of data and accelerating advancements in artificial intelligence and machine learning. 2. The significance of stable conductivity at higher temperatures. One of the standout features of the Northeastern discovery is the stability of the hidden metallic state at near room temperatures, which was previously achievable only at cryogenic conditions. This breakthrough is significant because it demonstrates that quantum materials can be practical for real-world applications without the burdensome requirements of extreme cooling. This aspect is often overshadowed by the sensational speed claims but is critical for the scalability of quantum technologies. Devices that require extensive cooling are not feasible for everyday use. Thus, the stability of these materials at higher temperatures not only makes them more applicable in consumer electronics but also reduces the energy costs associated with cooling systems, contributing to more sustainable technological solutions. 3. Entropy engineering and its broader applications. The UOW's introduction of entropy engineering to achieve the quantum anomalous Hall effect in a one-atom-thick magnetic material represents a significant theoretical advancement in materials science. While the immediate focus may be on the creation of a superhighway for electricity, the methodology of entropy engineering could have far-reaching implications beyond just this specific application. Entropy engineering allows for the customization of materials at the atomic level, potentially leading to the discovery of new classes of quantum materials with tailored properties. This could revolutionize not just electronics but also fields such as energy storage, magnetic materials, and even quantum computing. The ability to design materials with specific properties opens up a myriad of possibilities for innovation that might not yet be fully understood or appreciated. 4. Integration of conductive and insulating properties. Both research efforts highlight a trend towards integrating conductive and insulating properties within single materials. This integration is a game-changer as it simplifies the design and manufacturing processes of electronic devices. Traditionally, engineers faced the challenge of creating interfaces between different materials to achieve the desired conductive and insulating properties, leading to complications in device fabrication and potential points of failure. By using a single material that can switch between states, the complexities of engineering these interfaces are eliminated, which not only streamlines production but also enhances reliability and performance in electronics. 5. Implications for energy efficiency and sustainability. Both research studies emphasize energy efficiency as a key benefit of their findings. The UOW's work on creating a material that allows for lossless electricity flow along its edges could lead to devices that do not generate excess heat, a common challenge in current electronic systems. This reduction in energy loss is significant in the context of global energy consumption and sustainability. As electronic devices proliferate, the need for energy-efficient technologies becomes increasingly critical. The breakthroughs in quantum materials could contribute substantially to reducing the carbon footprint of electronics, making them more environmentally friendly and paving the way for a more sustainable future. 6. The role of quantum materials in future technologies. The advancements in quantum materials are not isolated events, they are part of a broader trend that reflects the growing importance of quantum technologies in various fields. As we approach the centennial anniversary of quantum mechanics, the implications of these discoveries resonate across multiple disciplines, from computing and telecommunications to energy systems and biomedical applications. The integration of quantum materials into everyday technology could lead to smarter cities, advanced medical devices, and enhanced data processing capabilities, fostering innovations that could reshape industries and improve quality of life. This broad applicability is often overlooked in discussions centered on speed and efficiency, but is crucial for understanding the transformative potential of these materials. Conclusion. The breakthroughs from Northeastern University and UOW signify much more than just advancements in speed and efficiency. They represent critical shifts in materials science that could redefine the landscape of electronics and other technologies. The significance of thermal quenching, stable conductivity at higher temperatures, entropy engineering, and the integration of conductive and insulating properties cannot be overstated. As the world increasingly looks toward sustainable and efficient technologies, these discoveries lay the groundwork for future innovations that could have far-reaching implications for our daily lives and the global economy. Recognizing these subtler yet profound aspects of the research is essential for appreciating the full scope of their potential impact. 1. Breakthrough in speed and efficiency. The research conducted at Northeastern University reveals a method to achieve a 1000% speed increase in electronics through the manipulation of quantum materials, specifically 1 by utilizing thermal quenching. This technique allows for rapid transitions between conductive and insulating states, enabling electronics to operate at terahertz frequencies rather than the current gigahertz speeds. This major leap signifies a potential shift from traditional silicon components to smaller, faster, and more efficient quantum materials, heralding a new era in electronic design. 2. Innovative control mechanism. The ability to control the electronic states of materials on demand is a significant advancement in quantum material research. The introduction of stable conductive states at practical temperatures represents not only a technological breakthrough but also a fundamental improvement in materials science. This allows for the simplification of electronic design by eliminating the need for separate conductive and insulating materials, thus streamlining the manufacturing process and reducing engineering challenges. 3. Complementary advances in quantum materials. Parallel research from the University of Wollongong introduces a novel method of entropy engineering to achieve the quantum anomalous Hall effect in a one-atom-thick magnetic material. This advancement facilitates electricity to flow along the edges of the material without energy loss, providing a highly efficient pathway for electrical conduction. The combination of these two studies illustrates the diverse approaches within quantum material research and their collective potential to reshape the future of electronics, particularly in developing energy-efficient devices, quantum computers, and other advanced technologies. 4. Significance for future technologies. Both studies underscore a pivotal moment in the evolution of electronics and quantum computing. With the centennial anniversary of quantum mechanics in 2025, these breakthroughs not only advance theoretical physics but also emphasize the urgency of developing energy-efficient technologies to address global energy consumption challenges. The potential applications range from everyday electronic devices that do not overheat to scalable quantum computing systems, underscoring the far-reaching implications of these discoveries in transforming the landscape of modern technology. 1. The Manhattan Project 1942–1945. The Manhattan Project was a research and development project during World War II in the United States that produced the first nuclear weapons. This project brought together some of the greatest scientific minds of the time, including J. Robert Oppenheimer, Enrico Fermi, and Richard Feynman. The project's goal was to harness nuclear fission to create powerful bombs ahead of Nazi Germany. The successful detonation of atomic bombs over Hiroshima and Nagasaki in 1945 marked a pivotal moment in warfare and international relations, leading to the Cold War and the establishment of nuclear deterrence. 2. The discovery of penicillin 1928. Alexander Fleming's discovery of penicillin marked a revolutionary moment in medical history. After observing that a mold, Penicillium notatum, had contaminated one of his petri dishes and killed the surrounding bacteria, Fleming recognized the potential for antibiotics. This breakthrough led to the mass production of penicillin during World War II, saving countless lives from bacterial infections. The discovery not only transformed medical treatments but also paved the way for the development of other antibiotics, revolutionizing healthcare and extending life expectancy. 3. The development of the Internet 1960s to 1990s. The creation of the Internet was a groundbreaking achievement in communication technology. Initially developed as ARPANET, funded by the U.S. Department of Defense, it aimed to enable communication between different computer systems. Over the decades, the Internet evolved, incorporating technologies like TCP/IP, which standardized data transmission. By the 1990s, the World Wide Web emerged, making the Internet accessible to the general public. This innovation transformed how people communicate, conduct business, and access information, fundamentally changing society and shaping the digital age we live in today. The recent breakthroughs in quantum materials research from Northeastern University and the University of Wollongong UOW herald a transformative era for electronics, with predictions that could reshape technology in the coming decades. These advancements, particularly in the manipulation of electronic states and the development of new quantum materials, will have profound implications for speed, efficiency, and utility in electronic devices. Key predictions for the future. 1. Massive speed enhancements in electronics. With Northeastern University's discovery of a 1000% speed increase in electronics through the thermal quenching technique, we can anticipate a paradigm shift in processing capabilities. Future processors could operate at terahertz frequencies, enabling unprecedented computational speeds. This will likely lead to new generations of devices that can perform complex computations and data processing tasks in real time, vastly improving applications in artificial intelligence, data analytics, and virtual reality. 2. Transition from silicon to quantum materials. As quantum materials like 1θs2 replace traditional silicon components, we can expect a significant reduction in the size and power requirements of electronic devices. This transition will not only enhance performance but also reduce heat generation, leading to longer-lasting batteries and devices that do not overheat. This shift may also stimulate the development of new semiconductor markets and manufacturing processes. 3. Energy efficiency and sustainability. UOW's research on the quantum anomalous Hall effect through entropy engineering points toward the creation of ultra-efficient electronic systems. The ability to conduct electricity without loss at room temperature could lead to devices that consume significantly less power. This will align with global sustainability goals by reducing the energy footprint of modern electronics and facilitating longer-lasting devices, which will be crucial as the world seeks to address climate change and energy consumption issues. 4. Revolutionizing quantum computing. The advancements in quantum materials are not limited to classical electronics. The new materials could serve as foundational elements for quantum computers, leading to machines that outperform classical counterparts by orders of magnitude in certain tasks. As quantum computing matures, we can expect breakthroughs in cryptography, complex problem solving, and simulations of quantum systems that were previously impossible. 5. Integration of light and electronics. The capability to control material properties with light represents a significant innovation in electronic design. Future electronics may incorporate photonic elements, allowing for faster data transfer and processing rates. This integration could lead to devices that seamlessly switch between states, enhancing functionality across various applications from telecommunications to computing. 6. Miniaturization and wearable technology. The ability to create smaller, more efficient components could spur the growth of wearable technology and Internet of Things (IoT) devices. As quantum materials enable more compact designs without sacrificing performance, we can expect an increase in smart devices that are both powerful and unobtrusive, enhancing user experience in everyday technology. 7. Broader impacts on health and medical imaging. The implications of these breakthroughs extend into the medical field. Enhanced imaging technologies could lead to better diagnostics and treatment options with devices that provide real-time data processing without the overheating issues that currently limit performance. 8. Global research and economic implications. As universities and research institutions worldwide invest in quantum materials, a competitive landscape will emerge, fostering collaborations and innovations that drive economic growth. Countries that lead in this field may gain significant advantages in technology and manufacturing, influencing global markets and industry standards. Conclusion. The discoveries at Northeastern University and the University of Wollongong represent pivotal moments in the field of quantum materials and electronics. As research continues to evolve, the predictions outlined here suggest a future where electronic devices are faster, more efficient, and capable of performing tasks that are currently unimaginable. The next decade will likely witness rapid advancements that not only enhance personal and commercial technology but also address pressing global challenges in sustainability and energy consumption. The 100th anniversary of quantum mechanics in 2025 serves as a fitting backdrop for these monumental shifts, marking the beginning of a new era in technology driven by the principles of quantum physics.